Try this in your head. Push a door right next to the hinge. Then push it near the handle, using exactly the same force each time. Why does one feel almost effortless, and the other feels like nothing's happening? The force hasn't changed. Something else has, and that something is about to become one of the most useful ideas in mechanics. Remember that a force is simply a push or a pull, and it always has both a size and a direction. You also know that many objects don't move in a straight line when pushed. They rotate around a fixed point instead. That fixed point is called a pivot, and a door's hinge is a perfect everyday example of one. Think about tightening a stubborn bolt with a spanner. Grip it close to the bolt, and it barely budges. Slide your hand further along the handle, and with the same push, it turns easily. The same pattern shows up with the door. Pushing further from the hinge makes rotation easier, even though your force hasn't grown at all. So here's the question worth pausing on. What two quantities, combined, must decide how strong that turning effect actually is? Take a moment before you answer. It isn't just the force, and it isn't just the distance from the pivot. It's the way those two things act together that produces the effect you feel. Physics gives that combined effect a name: the moment of a force. A moment is simply a measure of how strongly a force tends to turn something about a pivot. Every spanner, every door, every seesaw you've ever sat on is governed by this one quantity, built directly from the force applied and its distance from the turning point. The formal definition is moment equals force multiplied by the perpendicular distance from the pivot. Force is measured in newtons, distance in meters, and the moment itself comes out in Newton meters, written Nm. Notice the word perpendicular. It isn't just any distance to the pivot. It's the distance measured at right angles to the line along which the force acts. Picture a beam pinned at one point, with an arrow showing a force pushing down on it somewhere to the right of that pin. To find the moment, you draw a line straight from the pivot to the force's line of action, meeting it at a right angle. That short right angle line is the only distance the equation cares about, no matter how the beam itself is angled. Let's make this concrete. Suppose a force of 20 newtons pushes straight down on a lever, 0.5 meters from its pivot, with that distance already measured perpendicular to the push. The moment is force times perpendicular distance, 20 newtons multiplied by 0.5 meters, giving 10 newton meters. That single number tells you the full strength of the turning effect at that pivot. Here's a trap worth naming directly. If a beam is tilted, it's tempting to measure distance along the slanted surface of the beam itself, straight from the pivot to where the force touches it. That distance is not perpendicular to the force, so plugging it into the equation gives you the wrong moment. Always trace the right angle to the force's actual line of action, not along the object's shape. Now extend this to a beam balanced on a pivot, with forces pushing down on both sides. The beam stays level when the moments turning it one way exactly cancel the moments turning it the other way. We call this the principle of moments. The sum of the clockwise moments about the pivot equals the sum of the anticlockwise moments about that same pivot. Try a balanced beam with a 30 newton weight hanging 0.4 meters to the left of the pivot, and an unknown weight hanging 0.6 meters to the right. The clockwise moment must equal the anticlockwise moment. So the unknown force times 0.6 meters equals 30 newtons times 0.4 meters. That gives 12 newton meters on the left. So the unknown force is 12 divided by 0.6, which is 20 newtons. Balancing moments is only half the full picture, though. An object is truly in equilibrium only when two conditions hold at once. There must be no resultant force acting on it, and no resultant moment acting on it either. A beam could have balanced moments and still accelerate sideways if the forces on it don't cancel, so both conditions genuinely matter together. Before I say it again, see if you can state both conditions for equilibrium from memory. An object is in equilibrium when there is no resultant force acting on it and no resultant moment acting on it simultaneously. Miss either one, and the object will either accelerate or start to spin. Now push the model further into supplement level territory. What happens on a beam where two separate forces act on the same side of the pivot, while only one force acts on the other side? You can't just compare one force to one force anymore. You need the combined turning effect of everything on that busier side before you can compare it to the other. Suppose a 10 Newton force acts 0.2 meters from the pivot, and a 15 Newton force acts 0.4 meters from the pivot, both on the same side. Their moments are 10 times 0.2, which is 2 Newton meters, and 15 times 0.4, which is 6 Newton meters, adding to 8 Newton meters total. For balance, a single unknown force, 0.5 meters away on the other side, must also produce 8 Newton meters. So that force is 8 divided by 0.5, which is 16 newtons. You can demonstrate all of this with a pivoted meter rule and a set of hanging weights. Hang known weights at measured distances on each side of the pivot. Then slide them until the rule settles perfectly level. At that point, the clockwise and anti-clockwise moments have become equal, showing directly that a resultant moment of 0 is what equilibrium actually looks like on the bench. Let's gather the whole model in one pass. Moment equals force multiplied by perpendicular distance from the pivot. A balanced beam means the clockwise moments equal the anti-clockwise moments about that pivot. And true equilibrium needs both 0 resultant force and 0 resultant moment together, not either one alone. Go back to that door by the hinge. Pushing further away increases the perpendicular distance, which increases the moment for the same force, exactly as the equation predicts. A balanced beam, a tightened bolt, and a level meter rule are all the same physics, wearing different clothes. Moment equals force times perpendicular distance, and any object settles into equilibrium only once its resultant force and resultant moment both fall to 0. Next time you meet an unfamiliar lever or a loaded shelf, ask where the pivot is, measure the true perpendicular distances, and sum the moments on each side. That single check will tell you whether it turns or holds still.